All right, so does anyone recall the idea of standard deviation from last week? I hope so, because it's a big idea we're going to use this week. Anyone think they remember what it means? This is me patiently hoping somebody will.
Is that when we were talking about a measure of a spread from the mean, the average?
Exactly, yeah. Standard deviation is a measure of average spread. It's probably the best one in most circumstances. And the important thing about the spread is that it's from the mean, not the median. Oh, pen just freaked out. So it turns out standard deviation is useful for a lot of different things. In particular, if you ever take a full statistics course where you spend at least a quarter or a year on it, one thing you'll learn more about is inferential statistics, where we make predictions about things, like when they talk about a certain percentage of people agreeing with one idea. How do they know that? Because they didn't ask me. They didn't ask most people I know. So it turns out standard deviation is an idea related to that. Another idea related to that is the idea of a normal distribution. So I just want to go over some live data here. This is data I grabbed from the Oregon Health Authority, and they've been keeping track of and coordinating efforts to deal with the COVID-19 virus. This data I have here was, let's ignore the midpoint for a moment. From their website, they have age groups here, and they have the number of cases for each of those age groups. And so columns A and C together form what we call a frequency table. If we take over to the column D here, then this is the percents or relative frequencies. So as of yesterday, 18% of the cases were people 40 to 49, and another 18% were the people 50 to 59. If you have the data, it's easy to calculate the standard deviation or the mean. Now here, I didn't have the data, I just have a summary. So I had to guess by just using some messing around with midpoints of these intervals at the mean and the standard deviation. And don't worry about how I calculated those. That's a whole nother topic that's not part of this course, but based on the data, it appears the average age of a person who's been recorded with COVID-19 in Oregon is about 51 years old. And the standard deviation, meaning the average distance from that mean age of all of the others, is about 19 years. And so what does that look like graphically? So I tried to draw a picture of that over here. So here's a graph, and let's move this and that. Okay, it's a little better. Here is a histogram, and when you take a frequency table and you turn it into a bar chart, it's called a histogram. And we've played with histograms. We've also played with mean and standard deviations, so we're taking it a step farther now. You can see that the mean, I made another scale up at the top here to kind of represent the scale down here. I'm estimating 51 to be about here in the scheme of things. And if I take that standard deviation of 19 and I add it to 51, that's going to put me over here at 70. And if I add another 19, another standard deviation, that's going to put me over here at 89. So this mark right here is the mean plus 2 standard deviations. And I talked a little about this in the last session. Similarly, I could go the other direction. So from the mean, I could subtract 19, and I could subtract 19 again. And for most data, what we expect to happen is if we look 2 standard deviations to the left and 2 standard deviations to the right, and we count up how much of our data was in this case, between 13 years of age and 89 years of age, we should find most of the data. And the measure of most here is between 75 and 100%. So it's a pretty broad meaning of most in this case. And every data set's a little bit different. Some will be closer to 75%, others will be like 90, 95%. When I counted up based on guesses from their frequency table here, I estimated that about 1,879 of the people that got it were with between 13 and 89, which is around 96% of the people we've accounted for in Oregon so far. So that kind of goes along with that rule I was mentioning. The book talks about this idea, and I'm going to bring up the book here because this is a chart you may want to go back to. Where are you, book? There we go. So this is a common chart one could find on the internet, where it shows a smoothed out histogram where they just kind of drew a nice smooth line through what would have been stacks. And if they mark 2 standard deviations on either side of the mean, they say, yeah, about 95% should be in there. Now that's when they have what's called a normal curve. And I talked a little bit about that time, and I want to talk about it again. So there's all different kinds of shapes of distributions. And distribution, again, just means shape of a histogram. And so this one has a bell-shaped symmetric histogram. Just double check anyone else joined us, not at the moment. Other kinds of histograms are if I look at, let's see, did I do it on this one? Yes. I took a graph of the deaths based attributed to COVID-19 in Oregon as of the 21st, which was yesterday. And you can see here, this is not at all symmetric. It's not bell-shaped. And by symmetric, I mean we can draw a line through the middle, and the left side looks kind of like a mirror of the right side. This one's not a perfect mirror, but it's pretty darn close. I mean, if you think about your face, sometimes when you look at your face and you block the middle, the left side of your face looks quite different than the right. And if you were to mirror the left side to the right, you would look like a different person, or vice versa. But this is pretty close to a mirror image about the center. This one is totally not. This one has a clump of data over here on the right, and then a little tail on the left. Does anybody remember the idea of skew from the book or from last time? Would I consider this data skewed left or skewed right? Left. Yes, that is correct. Thank you for that contribution, Kayla. So again, if you don't want to talk and you don't have a microphone, feel free to chat. There's a chat that's going on here. Yeah, the skew is to the tail. And I'll try to show an example in a minute of why we call it that way. But yeah, this would be skewed left. So that rule about that the book shows about the 95% and the other percentages, that wouldn't apply to this because this does not have a symmetric bell shape. Would I expect about 75% of the data to be within 2 standard deviations of the mean? The answer is yeah, I'd still expect that. That's a whole different idea. So some other shapes, let's see, distribution, reviewing from last time. So this data set here would be one for if we watched somebody shoot free throws and let's say on average they get their free throws in 75% of the time. And then we let them take 12 shots at a time every day for a year. And then we just made a chart of how many times they got 9 out of 12 and how many times they got 8 out of 12 and how many times they got 10 out of 12. That chart would look something like this right here. 75% of 12 is 9, so we would expect they usually get about 9 of those shots in. Sometimes they had a bad day and they only got 4 or 5 in, or 6. And sometimes they had a really good day and they got 12 out of 12 in. On the other hand, somebody with a 50% free throw shot, we expect them to get half in, which would be 6 out of 12. And sometimes they get really lucky and get 9 or 10 out of 12, and sometimes really unlucky and get 2 out of 3 out of 12. This one right here is a very symmetric bell shape, whereas this one right here is skewed left because there's a little tail hanging out here on the left. Not all distributions have tails. Sometimes they're just weird, like this distribution here, where I have a lot of low values and a lot of high values, and then it's kind of symmetric about this low middle. This distribution is called bimodal. Mode is the most frequently occurring, and there are two groups here that have 25% of the data in them. So this has a dual mode, two modes, mode of 0 and a mode of 8. It is symmetric, it's not bell-shaped. And then the distribution in terms of like the 75% versus 90%, I would expect this to be more like 75% if we counted it up. But we would have to calculate the standard deviation to do that. And we'll do that on a set of data in just a minute. Hip replacements. Mostly it's older people that get hip replacements. So people in their 70s are most common to get them, and then people in their 60s. Very few young people get them. In this particular sample, nobody in their single digits or 20s needed a hip replacement at this time, and just a few in their teens. So this is an example of skewed left. Again, there are data sets that skewed right. I just didn't happen to put any in my sample here. This distribution here would be called uniform because everything's the same. So for example, if I looked at, let's see, what's a good one? If these were the days of the week down here, and I was looking at the amount of time I was awake, during a weekday, I'm awake about the same amount of time every day. So that'd be like a uniform distribution also. A distribution that would be skewed right. Let's see, I don't think I have one here, but I can make one up. If I were to ask people how far they commute to work, so distance, what I would expect to see is a bunch of people don't live too far from work. They're like 1 or 2 miles from work. Some people live a little farther, you know, maybe like 5 miles or 4 miles. And then there'd be very few people that live like 10 or 20 miles from work. Most people tend to live near where they work. And so if we were to make a histogram of this data here, what we should see is that the data is clustered to the left. Come on, Google. And there's a little tail to the right. So in this case would be an example of data that be skewed right because there's a right tail. Now, interesting thing about that tail, so we'll talk about why we say the skew is to the tail here. And let's calculate the mean of this distribution, these numbers, and the standard deviation. So spreadsheet's a nice tool for doing that. We just say, hey, I want the average, highlight the numbers. And for standard deviation, we have a whole lot of options. My recommendation last week was we use the STDEVS, which is more common on Excel, or just STDEV. P is for a population. Don't use that one because we rarely have a whole population. All right, so there's the mean, standard deviation, and then for fun, I'm also going to get the median here. And there's another measure of center. When the data is in order, we just pick the middle number. Okay, so I have a median of 2 when the data is in order. And double check I did that right. Yep. So if we were to sort this column here from smallest to largest, we should see that the middle number, sort range, oops, wrong button, sort range, this one. All right. So how many numbers do I have here? There are 15 numbers, so that means the 8th number is in the middle. So there are 7 numbers above this and 7 numbers below. 2 is the middle number. Notice the mean is quite a bit bigger than the median, and that's because of the skew to the right. The higher data is pulling the mean away from the median. So if this person said, I don't really live 20 miles away, I live 30 miles away, that's going to pull that mean even farther away. Okay? So a skew pulls the mean away from the median. It also in some sense distorts the standard deviation. And I'm using distort in a strange way there. Distort, sometimes people say is a bad thing, but it's actually a natural thing. Distortion happens all over the place. And so in this case, this person is so much different than the rest, it's making this data set look like it has a very wide spread. And it does, because it's that one number is way out there. So the skew is kind of related to the relationship between the mean and the median. Usually on skewed right, the mean is bigger, and skewed left, the mean is smaller than the median. Okay, let us play around with those percentile ideas. So I'm going to grab a data set from your homework. Where's your homework? Here we go. And this is problem 19. And I give you a data set, and I give you a histogram of it, and I say, hey, are there any outliers? So at this point in time, we have two ways to talk about outliers, and let's review both of those. I'm going to copy that into a spreadsheet, and apparently I need a new spreadsheet that's appropriate. Give me one moment. New sheet. All right, so this is math 213. The big topic this week. So here's all of my data there, and let's see, for Google to make a histogram for me, I need to get this stacked in one column, so I got to move stuff around. If I want to just calculate things like mean and standard deviation, it does not need to be in a column. I could have used that grid, that would have been okay. Almost done. And so I just want to reproduce that histogram because I want to be able to draw on it and do some other things. All right, and does this data set have a name? It did not. Oh, excuse me, I'm going to sneeze. Don't do it. All right, let's look at this one. Let's move away. So this is just data. And the quick histogram builder in Google is just highlight the data and then say, give me a chart. It might give me a histogram. Hey, look at that histogram. I'm going to zoom out just for a moment. So it picks some interesting divisions there. What did the homework pick? The homework picked nice numbers, 15, 20, and 25. So I can make Google do that by customizing the histogram. And let's go with 5. There we go. So that should look pretty darn similar. It looks the same. All right. So this is a histogram. Some data doesn't have a name, unfortunately. My apologies. Usually I pick more interesting things. And let's throw some titles in here so it makes a little more sense. The horizontal axis is just range of values. Ooh. And the vertical axis would be number of items. Okay, so that's a little bit better. We're just going to check out the outlier situation. So one way of measuring outliers for this is to find the 5-number summary, and based on the 5-number summary, you do that IQR rule. And we can go over that later if anyone needs to. I'm going to go over the second method, which was covered in the book this week. And the book called it the rare event rule, but it's the same idea, looking for outliers, and it uses standard deviations. So to do that here, I need to calculate the mean, because you can't have a standard deviation without a mean. And I want the standard deviation. So the mean, again, is the average. So you'll have to calculate that for this data set or the data set that you receive. And then you'll have to calculate the standard deviation, and we want the sample version. And again, select all the data. All right. So the abbreviation, the symbol for mean is X with a bar over it, and the symbol with standard deviation is just an S. I'm just going to put a little note here. I'm going to call this bar X, and I'm going to call this one S. It's just another label for each of those. Since this data has one, is accurate to the nearest tenth, the statistics should usually be calculated to the nearest hundredth. Oops, wrong way. So 2 decimal places. All right. So that would be an appropriate calculation for each of those. And then another search for outliers uses what we call the 2 standard deviation rule. Sometimes it's called the rare event rule. And to figure it out, what we do is we just look 2 standard deviations on each side. So if we look at the histogram, the mean is about 36, which is pretty much right in the middle, like it's supposed to be. Does this have a skew? Boy, that's a tough one. What do you think? Which side is the tail? Kind of leaning left. Not sure. What's the median here? Let's do a 5-number summary up here. 1. We have a vote on the skew on this. 3. Kayla agrees left too. I'm going to use quartile to make all these calculations. Data. Min, by the way, is also quartile 0. It would be quicker if I just cut and paste. 1. 2 is the median. 3 is quartile 3. And the max would be quartile 4. 4 quarters are all of the data. Median's 34.9, which is a little less than the mean. So if the mean is greater than the median, that's an indication that the data may be skewed right. There's a bunch of other ways to test skewness. Oh well, this one is a sketchy one, not a big deal. Anyway, back to the rare event rule. It says look 2 standard deviations on each side. So the lower bar for looking for outliers would be 2 standard deviations below. So that would be that bar X, my mean, minus 2 times the standard deviation. And so calculating that would be the mean minus 2 times the standard deviation. And the upper is 2 standard deviations above. So I just calculated from the mean over here, if I jump 1, 2 standard deviations, that's going to put me down here around 20. And on the other hand, if I go 1, 2, and get above, that should put me somewhere in the 50s. So upper, what I call bar X plus 2 standard deviations. Times S, it's about 50. So any data value that's below 20 or above 50 is considered unusual. It's rare for that to happen. It should only happen maybe 5% of the time or less. So let's check out this data. Is it in order? 17, 20, 33. Looks like it's in order. And is there anything lower than 20.89? The answer is yes. So let's mark that number. Let's yellow it, or let's make it orange today. And is there anything above 50.7? And the answer is Oh, darn, these aren't in order. Oh, because I messed it up when I redid it. All right, let's order these suckers. Data, sort range, no header. All right, so, okay, that is still the low one. I got lucky there. And on the upper end, we have one number. And every data set's different. Sometimes everything is within range, and there are no rare individuals in that one. So this number right here, we would say 53 is unusually high. Compared to sample data. And then this one up here, let's shift you down a touch, is unusually low. Sample data. So compared to all of the other numbers, this one's a bit low and the other one's a bit high. This is called the 2 standard deviation rule. All right. Let's see, what else do we need to do? Let's look at another example. Let's get a little more theoretical, sort of. What happened to my desktop? There we go. So we're going to look at standardized testing next. So with standardized testing, people study for these usually. So examples of standardized testing are like the, I can't remember the name of it now, what's the new test in Oregon for K through 12? Change the name every few years. Anyway, let's just put state assessments as an example. You all have to take those tests.
The Smarter Balance?
What's that? Oh yeah, Smarter Balance is the one they're using now, yeah. Thank you. And what's the one you all have to take for the ED program?
The CBEST, or which one?
Yeah, that's an example too. Is that just C like that? Something like that. And then SAT is popular for a lot, getting into a lot of schools. If you want to go to graduate school, you got to take a thing called the graduate record exam. And there's a bunch of other examples. In all these tests, people prepare for, they study hard for it, and they hope to do well. Now, what happens though, is not everyone does really well. There's this kind of, people tend to clump around some average, depending on the situation. So SAT, for example, on your page, SAT, the mean SAT score is about 1,000 total. And the standard deviation for SAT scores is about 200. Sometimes it's 210, but it's pretty darn close to 200. And a lot of people take it, people study really hard for it. And in situations like that, the results tend to give histograms that are pretty normal looking. So I'm going to borrow a normal distribution picture from elsewhere. I'm going to use StatKey today. And I linked to this in the videos and more section. I didn't link to the home page there. I linked to the theoretical distribution called the normal distribution. Now, normal distributions can be tall like this one. They also can be shorter. And that's just a matter of scale. Notice that the bottom scale goes 0, 1, 2, and there's pretty good distance between 0 and 1 and 1 and 2. Over here, we're going from 0 to 0.4. So this scale is stretched right here. So the size of this hump is a little bit distorted in this picture, but that's okay. It's just for educational purposes. I'm going to do a couple of things. First, I'm going to push the two-tail button, and this puts exactly 95% in the middle. And the numbers on the bottom here, the 0, 1, 2, those are standard deviations. So 0 means you're at the mean. This would be 1 standard deviation to the right down here, and this would be 2 standard deviations to the right. If we want exactly 95% of the data in the middle hump here, then that means we would be just below 2 standard deviations to the right and left. If I choose exactly 2 standard deviations to the right and the left, and I can change any of these by clicking on them. Since I'm doing the two-tail version, it matches that number on the other side with its opposite. So exactly 2 standard deviations on each side, if data is distributed normally, should be just over 95%. And notice in the tail here is about 2.5%. If you wanted a tail that was exactly 1%, you would just go there and type 0.01, because 1% is 1 out of 100. So to have 1% in the tail, that means you would have to be about 2.3 standard deviations to the left of the mean, is what this graph is telling me. And it takes a little getting used to doing this. There's a bunch of homework problems you got to do where you're trying to get used to these graphs. Let's go back to the 95 one. Oops, I'm going to enter it as a decimal. All right. In StatKey, you can't copy and paste these pictures. So if you want to use these pictures in the post, you have to do a screenshot. So in Windows, I would have to bring up the snipping tool and then get a new rectangular snip and click and drag over what I want to keep. So I'm going to call this one standard normal 95 in the middle, so I'll call it standard normal 95. So give it some kind of relevant name when you do a screenshot. And if you're not sure how to do a screenshot on your computer, let me know and I'll try to help you through that, because you may need to do that this week. So I got that picture. Let's get you out of the way. I'm going to put another one in my notebook. This other snipping tool. New page, please. And let's shrink you down a bit. All right, so I got this one here. I'm going to do another picture like this based on the SAT with a mean of 1,000 and a standard deviation of 200. So the cool thing about StatKey's tool is you can go to edit parameters here, and you can type in any mean and standard deviation you want. And this is going to be useful for activity 3 for this week. I definitely recommend using this tool. So I enter what I was given as the mean, which is 1,000. Standard deviation, which is, what did I say, 200. Hit OK. Now, the scale they pick on the bottom is not a standard deviation scale. It's not always going to line up perfectly. So that's just one caveat about this tool. It doesn't always line those up. Screenshot this. Should be good. Current page, and then, oops, wrong page. Control X. I want you on this page. Line these guys up. A little too small. Close enough. Okay. So the top here is what we call a standard normal, and I talked about this last week also. Standard normal distribution. And distribution just says it's some shape of a histogram. And this is a smoothed out histogram. All normal, oops, something went wrong there. Distribution, there we go. All normal distributions, something's not right there. I got some extra letters. There we go. All normal distributions have this bell-shaped curve. Now, some bells are taller and some bells are squatter. StatKey makes them all look the same, which is okay. The standard normal distribution has a mean which we call x bar of 0, right in the middle, and a standard deviation, which we call S usually, of 1. The standard normal distribution is also the distribution of z-scores, which we started talking about this week. So distribution of z-scores. And all a z-score is a count of standard deviations. So z-scores count standard deviations. So for example, if I took the SAT and I scored an 800 on the SAT, so that's what this one is for. If, let's see, x bar for the SAT is about 1,000 points and the standard deviation is about 200. So if x, some score, mine, is equal to 800, that puts me right there. Okay. I am 1 standard deviation below average because the average is 1,000 and I'm 200 below 1,000. So what should my z-score be if my score is 800? Anybody want to take a guess? This one is nice. It happens to line up quite nicely. Shall I repeat the question? What would my z-score be if I have a score of 800? Am I all alone again? Is anybody with me? Hello? I think I lost.
Would we?
There we go. Giselle, hey.
Hello.
What's up?
So we're counting the distribution of the z-score from the actual standard deviations on, or from the average?
From average. So I'm 200 below average. How many standard deviations below average am I? So
1.
1, yeah, there you go. I'm exactly 1 standard deviation below average. And the z-score just counts. -1 means 1 below. If someone had a score of, say, 1,400 on the SAT, so if this was their score down here, oops, that's not a line, try again. Then they would be +2 standard deviations. Their z-score would be 2. Now, again, I like thinking about standard deviations in the very simple way is it just counts standard deviations. So if you know the mean and you know the standard deviation, you can kind of estimate it, okay? So here's 1,000, that is the middle, that is my x bar, oops, not a pen. So x bar is the 1,000, that's exactly in the middle here. And the score of 1,400 is 200 plus another 200 above. So that's exactly 2 standard deviations above. Now you could be a fraction of a standard deviation above. So for example, if somebody had a score of say 1,500, which would be right down here, let's mark that. How many standard deviations are they above average? Anybody want to take a guess?
Is it 2.5?
Yeah, they'd be 2.5, right? Because 3 full standard deviations would be 200 plus 200 plus 200, which would take us to 1,600, and 1,500 is like halfway from 14 to 16. So when you draw a picture, and I like drawing pictures with these, it helps me figure it out. There's formulas too, which are nice. So the formula for a z-score is to take whatever number you were given, somebody's score, subtract from that the mean, and divide by the standard deviation. So remember, the distance from any value to the mean, that top number is called the actual deviation. And deviation just means distance from center. So this top number is the deviation. Not standard deviation, just a single deviation. And when we divide S into someone's deviation, we're just basically saying how many times does S go into your distance, right? Which counts how many S's are in D. So if we test that out for the X equals 1500 down here, so if we say X, somebody's score on the SAT is 1500, and we want to know what their Z-score is, then we would take 1500, subtract the mean of 1000, and then divide by 200. Okay, 1500 minus 1000 is 500. 500 divided by 200 is 2.5. So their Z-score is 2.5, meaning they are 2.5 standard deviations above average. So is that person unusual, or are they pretty normal to get a score of 1500?
I would say above average, like.
Well, it's definitely anything above 1000 is above average. But is it unusual?
No.
No? Okay. So what's our measure of usual? We have two measures for usual. One is using the IQR. Now we've got nothing about quartiles here, so we're not going to use that. The other is that new rule, the two standard deviation rule. And the two standard deviation rule says if you have a measurement that's more than 2 standard deviations from average, it's unusual. Okay. If you look up here at my numbers, this 0.95 up here means that 95% of a population that we believe has a normal distribution should be within 2 standard deviations of average. So that means what percent of the population is above that? This right here says about 2.5% of the population is above, and about 2.5 is below. So this person right here is in the top 2.5% of all people that take the SATs. So is that unusual? The answer is yes, it is unusual. Most people we meet fall in this region right here. Very few fall way out to the right and way out to the left. So that would be unusual. To take a closer look at how unusual that is, let's go back to that calculator here. So I want to figure out how unusual it is for someone to get a score of 1500. So to do that, I'm in my theoretical distribution calculator for a normal distribution. I have to make sure my parameters are set to the correct mean and standard deviation, which I already did. In this case, I'm going to go for either a left tail or a right tail. I'm going to do the left tail for fun. And then I type the number I'm interested in. Since I'm interested in someone's score, their score goes on the x-axis. So they got a score of 1500. And this tells me here that they did better than 99.4% of people that take the SAT. That's pretty amazing. I don't know many people like that. I definitely didn't score that high on the SAT. So that's pretty high. What percent of people are on the other side that did better than this person? Well, we would just subtract this from 100%, or we could just switch to a right tail. So this tells me less than 1% of people did better than that, but switching to a right tail, it'll just give it to me. So this says 0.0062. Change that to a percentage, you would shift the decimal point twice. So that means about 0.6% of people, less than 1%, about 0.5% of people did better than this person. So that's a pretty unusual person. They're pretty outstanding there on terms of the SAT. So back to my notes page. Let's use red. So in this tail here, there's some people, And the percent of people that live after the score of 1500, people that got a score of higher than a 1500, is 0.6% about. Okay? Less than 1% of people scored better than 1500. Let's suppose somebody had a score of 700. So it's getting a little messy, so let's get a new page. Copy, paste. All right, so this is still my SAT graph here, and let's blow that up a little more. So we have X bar, put it down here, is the 1000, and we have S, our standard deviation, is 200. And let's suppose some person now has a score of 700. So what we want to do is we want to give this person some information about the score. Like, what would the College Board write back to them about their score? Well, they might give a graph saying, hey, the average person scored 1,000 and the average spread is about 200, right? Because remember, standard deviation is a measure of average spread from the middle. And so we could make a mark here. X marks the spot, and saying your score was 700. So that's you. What does that mean? Well, we can calculate a z-score. So let's see, one standard deviation to the left would be 800. Two standard deviations to the left would be 600. So guess at about what their z-score is. Is it -1? Is it -700? Is it +1? Nobody wants to guess. Come on, you guys. I'm so lonely over here. So let's see. One standard deviation below would be 800. So 800 would have a z of -1. -1.5. Agreed. Yeah, they're right in between 1 below and 2 below, which would be -1.5. And if we plug it into the z-score formula, then we get 700 minus 1,000, which is the average, divided by 200. That would be -300 over 200, which would be -1.5. Exactly. So their z-score, that's a z, is -1.5. Okay, so we might give them a z-score to say you are 1.5 standard deviations below average. That's what that means. Is that good? Is that bad? Is that unusual? Well, good and bad are judgment calls. Unusual is not. We can measure unusual. So something would be unusual if it's more than 2 standard deviations on either side. Now, 2 standard deviations to the left would be 600. So 600, the z-score would be -2, because that's exactly 2 standard deviations to the left. This score is not that far to the left, so it's not unusual, okay? This is not unusual. We could console them. Some people aren't happy about being below average. Now, that kind of depends on the situation. For example, our Oregon's death rate related to COVID-19 is not as high as other states. We have a lower death rate. That's good, right? We're glad to be below average there. So below average is, again, a judgment call. In this case, we kind of wanted to score high because we're hoping to get into a certain school. So some other things we could do is we could tell this person what % of people did better than them and what % did worse. So by that, we would want to count how many people, oops, that's not a scribbler. There's the scribbler. How many people live over here below 700, and then how many people live above? The people that live below, so if I wanted to calculate the % below, that value is called a percentile. So often when you take a standardized test, you're given your percentile. Sometimes they give z-scores, sometimes they don't. That depends on the test. But they always give a percentile. So let's give the percentile for this person. For that, we have to calculate it. So I need a standard distribution, a normal distribution calculator, and stat key is a good one. You can do this in Excel too. It's a little bit more work. This one I like because it shows us pictures. So in order to use the calculator, we need to make sure we have the correct mean and standard deviation. If not, we edit and put them in there. And then a left tail is a percentile. So then I click the left tail button because percentile is always the percent at or below. So this says if you got a score of 608, you'd be in roughly the second percentile. So this is 2.5%, so you're somewhere between the second and third percentile. If a person has a score of 700, we just go down to the bottom, click, type 700, hit OK, and then we get 0.067 is the decimal version of the percent. So coming back to my picture, the percent below here was, the decimal was 0.067, which equals 6.7%. And again, it differs on each company that gives these tests and how they do their reporting. They might just round it and say something like, you scored better than about 7%. A more specific thing to say is a score of 700. And my pen's got some delay here. Score of 700 is the 6.7th percentile, meaning about 7% of people scored less than this person right here. Okay. Now, the downside of that is 95.3%. No, what is that? I got that wrong. 93.3% of people scored higher. So would we recommend this person study more? The answer is yes. They probably should go back and study quite a bit harder and hope to get a higher percentile. What if they scored 1,000? If somebody had a score of exactly 1,000, what would their percentile be? So X equals 1,000. What percentile is this? So if I draw a line at 1,000 and I look at my graph, what percent of people are below this line in the histogram? Hoping for a response. Can I respond to myself? Is that legal? Let's make it legal, 50%, because it's the mean, and the mean is the middle of a normal distribution. So I would say a score of 1,000 is the 50th percentile. That's abbreviated as P100. Oh, P100, 50%. So a score of 1,000 marks the 50th percentile. And we kind of did percentiles last week with quartiles. For example, what number marks the third quartile? So that would be somewhere probably over here-ish. Q3. So the third quartile, 3/4 is 75%, would be the 75th percentile. And I can easily get that from stat key. by choosing left tail and then changing the percent to be the percent I want. So I want 75%. What score goes with that? So this says if you get a score of 1,135, you would be in the 75th percentile. So 1135. So for the SAT, given its mean and standard deviation, the third quartile, the 75th percentile, would be a score of x equals 1,135 approximately. So if that was your score, 75, you did better than 75% of people that took the test. All right, it is 4 o'clock. We are at the edge of time today. Does anybody have any questions that they want to ask about this week? We have slightly less assignments this week. Let's take a look here. Week 3, I added the learning forum, so I would like you to write about something you learned. You know, the easiest thing to do for this right here is when you're working on a homework problem, and if you got stuck on this right here, then post your question about this to the forum. That would be an excellent use of that forum. Say, hey, I got stuck on this problem. Can somebody help me with it? And if somebody doesn't respond to you within 24 hours, I'll jump in and respond. But that would be a good use of the learning forum this week. And there are several tricky questions this week. Super important. Do all of the homework and have watched the videos and done the reading before you do the activity. So the activity is not like the homework where you can do it over and over and over again. You only get one shot at it. So this activity is like what we were just playing with, SAT scores, but this one is about reading scores. Each person's will be a little bit different. So I'm just gonna grab this text. Yours will be slightly different. Let's see, I want it in my whiteboard, which is over here, and there, and there. So the scenario is the same, but the numbers are different for each of you. And blow that up. So suppose you're an elementary school teacher, which most of you are hoping to be, and you were evaluating the reading levels of your student. So you find an individual that you're working with, they read 36.3 words per minute on average. You do some research and determine that reading scores for their grade are normally distributed. That means they fit that symmetric bell-shaped pattern with, in my case, for my grade level, it was a mean of 80 and a standard deviation of 32. So then what I would want to do is, and I'm just going to draw this in here, and you could draw it by hand. I'd recommend using a standard distribution calculator. So I'm going to draw my best bell curve. Wish me luck. Hope it goes better than my circle in week 1. Not too bad. All right. And the middle is about right there. So for my grade level here, I'm told that the mean, or X bar, is about 80 words per minute. And the standard deviation, S, is 23 words per minute. So 1 standard deviation to the right would be about here. 2 would be about here. 3 would be about here-ish. So that would be what, 103 there, and 126 would be here. Third standard deviation, if I go the other way, 1, 2, 3, 1 standard deviation to the left would be what, 80 minus 23 is 57, minus another 23 would be 34. So what we would expect is this is 1 standard deviation to the left, right? So that would have a z-score of -2. This one would be, 2 standard deviations to the left. This would be 2 standard deviations to the right. So this score would have a z of 2. Does anybody remember what % of scores should be within 2 standard deviations if the data is normally distributed? I think I lost my audience. What % of data lives in the middle? Oh, Peter's whispering something to me. Peter says 95. Thank you, Peter. 95% of the data lives within 2 standard deviations. Okay. And then just 2.5 lives out in each tail if you're talking about 2 standard deviations. So if I have a student had a reading score of 34, that means about 2% of kids read slower than them. So we would want to help that person catch up. So your goal for this problem is to figure out what percentile your student is in based on the average and standard deviation for their grade, and then have a picture of what that means, and then try and explain this to a parent. So you're going to write up an explanation, and then I have some tips on what needs to be in your explanation there. Here's where you upload your graph. I recommend using a calculator for it, like StatKey, where you can type in the numbers that you want, or you could try to do like I did and draw it by hand. I drew more than I needed to. I was just kind of playing around here. All I really need to draw in is the mean, standard deviation, and their score, and then their percentile. So that is a tough problem. So again, check with each other on that. And if you get stuck on the homework, in addition to hitting message your instructor, be sure to post to the forum, because you can get credit for that too. So you ask a question and get credit. All right, that's it on my side. Unless you guys have further questions, I'm going to sign off and get some exercise before dinner. Thanks. Bye, y'all.